Valence bond theory, treating how covalent bonds form in molecules. The purpose of valence bond theory is to examine the way that molecules come together from orbitals and then how those orbitals relate to actually creating a molecular geometry and combining together to make bonds between atoms in an element. The idea of valence bond theory operates on what we call orbital overlap. If I take orbitals within an element and mix them together or mix them with orbitals from another element, I can create either hybrid orbitals or molecular orbitals that will hold molecules together. Now, orbitals come in different kinds. There are what we call pure orbitals, and these are straight atomic orbitals like s orbitals, p orbitals, d orbitals. A hybrid orbital is an orbital that is created by mixing orbitals. So I can combine an s and a p orbital and make an sp orbital, or combine an s, a p, and another p and make an sp2 orbital. These hybrid orbitals are frequently used in bonding in molecular configurations. Now, looking at bonding, there are multiple types of bonding that we deal with, right? There are single bonds, there are double bonds, there are triple bonds. A single bond is called a sigma bond. Any first overlap between two atoms is a single sigma bond. If I'm forming a multiple bond, like a double bond or a triple bond, these bonds are called pi bonds, and they occur from p orbital overlap. While a sigma bond can be formed from overlapping pretty much any orbital, pi bonds form from the overlap of p orbitals. Hybridization is a process by which we actually mix these orbitals together, as we said, and so getting orbitals that are not standard s or p, but have characteristics that are a mixture of, say, s and p orbitals or sp and d orbitals, depending upon what goes into the hybrid. The number of orbitals that we get out of a hybridization process is equal to the number of orbitals that go in. So if I have an sp2 orbital, for instance, I have an s and two p's, so I get 3 sp2 orbitals out of that hybridization process. And all the orbitals in a hybrid series are degenerate. They are all the same energy. While an s orbital and a p orbital are different energies, the mixture of the s and the p orbitals together creates degenerate orbitals of the same energy. Hybridization occurs when atoms lack half-empty orbitals that they can use to overlap and make bonds. If I can't put electrons into an orbital because all the orbitals are filled, then I cannot make a bond between them. Now, if I look at beryllium chloride, for instance, beryllium chloride is in this issue. Empirically, the molecule, according to physical evidence we've been able to obtain, has chlorines that are equal to each other. There's no difference between the two chlorines in beryllium chloride. Looking at the valence orbital diagrams, which is just the valence electrons of beryllium and chlorine, we find beryllium has 2 electrons occupying the 2s orbital and none in the 2p, where chlorine has 2 electrons in the 3s and 5 electrons among 3 3p orbitals. Beryllium lacks any half-filled orbitals with which to bond. Chlorine has 1 half-filled orbital that it can use in bonding. So one idea then would be to take the electron that is in the 2s orbital in beryllium and promote it or move it up to a 2p orbital, which would give you 2 orbitals that were then half-filled. The problem with that then is you now have, while 2 orbitals that are half-filled, they are not degenerate, they don't have the same energy. So you have to find a way to get orbitals that have the same energy. In order to do this, we wind up mixing orbitals, creating hybrid orbitals through hybridization. Mixing orbitals causes us to create orbitals that have characteristics of both orbitals that were mixed, or all the orbitals that were mixed. For instance, the sp orbital, which would be made from mixing an s orbital and a p orbital, has characteristics of the spherical s orbital and the somewhat figure 8 shaped p orbital. We have a large lobe that's somewhat like that sphere, but it's also got a tail off of it, so it still has something of the figure 8 appearance from the p orbital. The hybrid orbital diagram for beryllium illustrates the sp orbitals that are formed from combining an s and a p orbital together. And we see that these are both degenerate and intermediate in energy between the p and the s where they came from. I can overlap the beryllium sp hybrid orbitals and the chlorine p orbital and make bonds. So the 2 chlorines can each overlap a p orbital with the beryllium sp, and if you look at the way that it's drawn out, the little light blue represent the tail. Each one corresponds to the opposite darker blue lobe in the same way that you see the sp over on the right. So this overlap then creates a bond between beryllium and chlorine. Now, hybrid orbitals are based on the mixing of the orbitals that go in. The central atom of my molecule will determine what I need to hybridize. Standard geometries will exist with, for instance, two densities. We'll create an sp because I need to have two orbital mixing in order to get two densities out of that for bonding. So if I'm mixing two, I mix an s and a p. If I move on to needing three densities, something that's trigonal planar rather than linear, I will have three orbitals that are needed to mix in order to get three half-empty orbitals. And this will create sp2. The 2 means that I'm using two p orbitals with the one s. Four densities requires the use of a total of four orbitals, so something like a tetrahedral would mix an s and three p's, so an sp3 orbital. And the geometries that we associate through VSEPR theory and other theories with molecules match up with the densities we get from these hybrid orbitals. A 180-degree angle is what we would expect between two orbitals trying to keep away from each other, 120 degrees between three orbitals trying to keep away, 109.5 when in a spherical density between things trying to keep away with four. If we move on to the octet exceptions, the 5 densities requires 5 orbitals. Now we're out of orbitals with s and 3 p's because the p subshell only has 3 orbitals. To get a 5th orbital, we have to reach into the d orbitals, and this is why something like a trigonal bipyramidal only occurs in an sp, or the trigonal bipyramidal only occurs in atoms that have access to a d orbital, so we can get sp3d, for instance, like trigonal bipyramidal does. These molecules will have orientations that have 5 areas of electron density, mixing 5 orbitals and getting the sp3d with 10 electrons in them. If I get 6 electron densities, I wind up with an octahedral configuration where I wind up with sp3d2, a total of 6 orbitals. We have to reach into 2 d orbitals in order to mix a total of 6 and get 12 electrons out of that. Now, electron geometry configurations occurring from hybridization. Hybridization itself is independent of bonding. You're not going to necessarily have hybridization in a molecule. Most molecules do, but not all. Hybridization applies anywhere where the number of degenerate orbitals that we need are less than those that are available based upon the actual atomic orbitals involved. Something where I have a lone pair can also exist in a hybrid orbital. If I look at ammonia, NH3, there are 3 H bonds and a lone pair in that molecule. The NH3 molecule has a tetrahedral electronic configuration. It has an sp3 hybrid configuration. And of those 4 hybrid orbitals, 3 bond to hydrogen, the 4th accepts the lone pair. In other instances, though, something like phosphorus trihydride simply overlaps 3 p orbitals with the HS orbitals, and the lone pair resides in the s orbital of the phosphorus instead. We always must base our theory on empirical evidence from experiment. Experiment always trumps theory. Experiment always comes first. So looking at phosphorus trihydride, the angles between the hydrogens are about 90 degrees, more consistent with simply orienting 3 p orbitals together. So we don't apply VB theory or VSEPR theory as much to that molecule because the evidence doesn't suggest it. Electrons obey the same rules in valence bond theory that they do with VSEPR. Repulsion orients the orbitals together. If I look at a linear orbital, for instance, there are 2 orbitals there, and they form 180 degrees between each other. Looking at a tetrahedral configuration with 4 orbitals that are hybrid orbitals, they make 109.5 oriented at the corners of a tetrahedron. Now, multiple bonding occurs in situations where I have overlap from not just hybrid orbitals, but p orbitals as well. Some molecules will make multiple bonds. Some will make double bonds, some will make triple bonds. A sigma bond always comes first. The sigma is a single bond. Hybridization is based on configuration. So if I look at something like ethene, the geometry is trigonal planar. Each of those carbons forms a central point, and the hydrogens connect to them. A trigonal planar geometry has 3 densities: carbon bonded to another carbon, carbon bonded to hydrogen, and carbon bonded to another hydrogen. So those 3 densities then warrant an sp2 configuration. If carbon has an s and 3 p's, sp2 uses up s and 2 p's, which leaves 1 p left over. the carbon and hydrogen orbital diagrams, we see hydrogen has a single electron in the 1s orbital, carbon has 2 electrons in the 1s, 2 in the 2s, and 1 each in 2 of the 2p's. If I'm going to mix the 2 of the p's and 1 of the s's, I have 1 leftover p, which contains 1 electron. So there are 3 2sp2 orbitals that are available for bonding, and 1 of those bonds to the other carbon, making a single bond, 1 of those bonds to a hydrogen, and the last bonds to the other hydrogen. That leftover p then still has to make some sort of bond. If we look at the actual structure of the molecule, the hydrogen will overlap its 1s with the c hybrid orbitals that are left over. So we get hydrogen overlapping with a hybrid orbital in each of the sides, and then the carbon overlapping its hybrid orbital in between the 2 carbons. Those leftover p's will mix together and make a pi bond. That half-full p orbital then mixing with a second half-full p orbital makes a full orbital mix from the 2, and we get bonding. This is, look, if you imagine the diagram here, this is the same diagram that's on the right, but flipped now in a rotation, so that we're looking at it side on. The yellow and the orange are the p orbitals from the 2 carbons respectively, and they overlap where the kind of brownish gray color is, which makes not a single solid spherical density like we get from a sigma bond, but 2 densities which have a hole between them in a p orbital, in a pi bond. If I had a triple bond, I would then have a second set of p orbitals sticking out directly at you from the computer, and those second set of p orbitals would make another one of these semi-hollow orientations, so that I would have 2 sets of p orbital overlap. So in summary, hybridization is relative to geometry. A linear geometry has 2 densities, and so linear geometry you would expect to be SP. A trigonal planar would be SP2, a tetrahedral SP3, trigonal bipyramidal SP3D, and octahedral SP3D2. Multiple bonding will occur in cases where I have a free half-filled p orbital that can overlap to make pi bonds. You will always make a sigma bond before you make a p orbital overlap in a pi bond. If I have a double, I'll usually get an sp2 configuration in a molecule with a double bond. If I have a triple, there's 2 p orbitals available, so I'll generally get an sp configuration there. Looking at a summary of the geometries, the orientations of the hybrid orbitals, linear has the 2, trigonal planar the 3, tetrahedral the 4, trigonal bipyramidal has 5, and octahedral has 6. If you look at this particular illustration, the book actually has this mixed up. They've got the 2 hybrid orbitals from trigonal bipyramidal and octahedral flipped, because you notice there are 6 for trigonal bipyramidal and 5 for octahedral. So that one's backwards from how it's supposed to be. The orientation of the angles is as we expect. It's the same as it is in VB theory as it is in VSEPR theory. So overall, the 2 theories work well together.